We can also mathematically describe what's going on here other than just graphing it. So if we want to look at the mathematical equation of a wave, we want to describe, again, as I mentioned, what we're describing is the electric field. We're not worrying about the magnetic field here. As a function of x and t, that's equal to a cosine 2 pi x over wavelength minus 2 pi nu t. And note that this is the Greek letter nu. This is not a v. Where we have E, which is equal to the electric field. What is x? Yep, the position of the wave. And what about t? Yeah, so we're talking about both position and time. So what we can do if we're talking about a wave is think of it both in terms of position and time. But if we're trying to visualize this, for example, if we're actually to graph this out, the easiest thing to do is keep one of these two variables constant, either the x or the t, and then just consider the other variable. So for example, if we're to hold the time constant, this makes it a lot simpler of an equation, because what we can end up doing is actually crossing out this whole term here. So what we're left with is just that the electric field as a function of distance is a times cosine of the argument there, which is now just 2 pi x over wavelength. So what we want to be able to do, either when we're looking at the graph or looking at the equation up there, is to think about different properties of the wave. For example, to think about at what point do we have the wave where it's at its maximum amplitude. So if we think about that, we need to have a point where we're making this argument of the cosine such that the cosine is going to all be equal to 1, so all we're left with is that a term. So we can do that basically any time that we have an integral variable that is either 0 or an integer variable of the wavelength. So for example, negative wavelength or positive wavelength or 2 times the wavelength, because that lets us cross out the term with the wavelength here, and we're left with some integer multiple of just pi. So that's sort of the mathematically how we get to A, but we can also just look at the graph here, because every time we go one wavelength, we can see that we're back at a maximum. So I mentioned we should be able to figure out where the maximum amplitude is. You should also, just looking at an equation, immediately be able to figure out what that maximum amplitude is in terms of the height of it just by looking at that A term here. We should also be able to know the intensity of any light wave, because intensity is just the amplitude squared. So we should immediately be able to know how bright or how intense a light is just looking at the wave equation or just by looking at a graph. We can also do a similar thing, and I'll keep my distance from the board, but we can instead be holding x constant, for example, putting x to be equal to 0, and then all we're doing is considering the electric field as a function of t. So in this case, we're crossing out the first term there, and we're left with amplitude times the cosine of 2 pi nu times t. And of course, we can do the same thing again. We can think about when the amplitude is going to be at its maximum, and it's going to be any time cosine of this term now is equal to 1. So that will be at, for example, negative 1 over nu, or 0, or 1 over nu. And again, we can just look at our graph to figure that out. That's exactly where we're at a maximum. So 1 over nu is another term we use, and we call it the period of a wave. And the period is just the inverse of the frequency. And if we think about frequency, that's number of cycles per unit time. So for example, number of cycles per second, whereas the period is how much time it takes for one